again, so let's have some fun and talk about protein chromatography like a museum. Not that protein chromatography isn't fun as it is, and it allows us to purify proteins, but we can conceptualize this by thinking like we're sending a bunch of protein babies through museums. And so I call them babies because we get so used to working with the proteins that we love that we can think of them as like our little kids, and we take very, very, very good care of the proteins that we're purifying. But they're hanging out with a bunch of other kids, and we want to get them alone. So we send them through different museums, and they'll travel through at different rates, and then they'll come out and they'll get on the bus that are like fraction collector, and then we'll pick them up, and our protein's all alone, hopefully. We don't want to take their friends home because they smell.
If you want really serious content on chromatography, you know I'm good for that. But today, I thought let's just do a fun chat. So protein chromatography is this way that we can purify proteins by sending them through these columns filled with these little beads called resin. And we can do it in these gravity flow format or using this machine called an ACTA, it's like FPLC machine. The basics is that inside these columns are these little beads, these little resin beads, and they have different properties. If you take a solution of proteins and you flow them through these columns, the proteins since the proteins have different properties, they're going to interact differently with the resin. And so they're going to come out at different times. We can get them to do things like stick and unstick with affinity chromatography methods and ion exchange chromatography methods, basing on their charge with ion exchange. Or we could just separate them by size by sending them through beads that have pores that they travel different speeds through. So that's a more serious look when we can do a workflow. If we want to get a protein really, really pure, we can do a series of steps in a row, chromatography steps in a row. So for example, we often start with some sort of affinity chromatography, some sort of capture step. Maybe we've expressed our protein recombinantly. So we stick the instructions for making it into cells and have them make it for us. Since we're telling them what to make, we can have them make a little extra on the end that can serve as an affinity tag that's going to bind to resin that's specific for that. And then we can get our stuff to bind, then push everything else off. We can take advantage of things like the protein's natural charge. So even if you don't have that specific tag, you can get it to stick to resin based on its charge. And then we can do things like size exclusion, where we're separating based on their size, because these the bigger things don't have to go through all of the tunnels because they can't fit. So the little things are going to have to travel further, and so they're going to go slower. So that's the more serious look. And if you want a more serious look at all those different steps, I have videos, I have posts, I have graphics, I have everything, because I really, really love protein chromatography and I've done a ton of it. But for today, let's go to this museum analogy, because I'm getting nostalgic as I'm finishing up my PhD work. Well, I mean, I finished my PhD, but I'm just finishing up the research for the project, finalizing things for the paper, that sort of thing. And so last week I purified this protein for the last time, and I must have purified it hundreds of times. And so it was a little nostalgic because I think of these proteins as kind of like my little kids that I want to take really good care of and isolate. I'm a very protective protein mother. But so I came up with this analogy a long time ago, where basically your little protein kid is actually trapped with a bunch of other kids. So they're in like a schoolhouse. And we want to just pick up our kid. We don't want to pick up those other kids. And so this is like your protein in a cell. There's one that you want, but then there's a lot of stuff that you don't want. So what we can do is we can send these proteins on a field trip. So we send them through museums. So these like protein chromatography columns are kind of like museums. Then the kids are going to spend different times in the different museums based on like how much they like the experiments, how much they like the exhibits, or how many exhibits they, so that would be like affinity chromatography, or how many exhibits that they go to, which would be like a size exclusion. And so we can send them through these, and then because the proteins are going to be traveling differently through the column, they're going to come out at different times. And if you say we have like a bus schedule where a bus is coming every hour, and it'll pick up the ones that have come out. So this is kind of like our fraction collector. So for example, with this ACTA, this protein purifying machine, the sample is going to come through and it's going to go into this fraction collector where we can collect them. So this would be like the buses then arriving. at your house or at wherever the school, wherever you're going to pick them up from. And so let's talk more about these different types of museums that we can send them through. So the museum walls are really boring, but the exhibits and the placards and stuff, those are really exciting for some people, but not for others. You can think of them kind of like classified ads on a billboard. And so your like the basics of the like the beads, so these are typically made of some like sugar, like agarose or dextrin or some combination of them, and something that's chosen because it's like sturdy and you can make this mesh out of it, but they're kind of blah. And so these are going to be in size exclusion chromatography. It's like you have empty cork boards. There's no classified ads on there. These museum walls are empty. But you can tack on ads by covalent linkage. So basically covalent linkage is when something's permanently stuck on there, and instead of like the proteins that might come on or not on. And so you can do this, you can add things that specific proteins like. And so it's kind of like adding classified ads for that specific thing. So for example, if you have a strep tag on your protein, that would be like a classified ad, streptactin resin-seeking biotin. And so that's its natural binding partner, but then we'll settle for strep tag 2 or just thiobiotin. And so the strep tag is what is the tag on the protein, and then the thiobiotin is the competitor we'll send in later. Then but if you had something that say had a his tag on it, now it wouldn't be find anything on this billboard, it wouldn't find anything on those beads, but here it's going to see that nickel is seeking nucleophiles willing to loan electrons, and his tags wants his tags to stop and coordinate with it. And so his tags, the histidines, can coordinate with nickel metal that's stuck to the beads. And so this would stick to these beads. And then finally, you can have something like glutathione, agarose, that's seeking GST if you have like a GST tagged protein. And so this would be kind of like having museum exhibits that you are stuck at. And sorry for mixing analogies there. So in affinity chromatography, this is like where we have like some unique feature like an affinity tag. So here the museum is going to be like perfectly suited for that person. They're going to be really want to stick to it. And so it's like having exhibits that you really love and like only you would really love. So I'm guessing most people aren't as excited about protein purification as I am, or my like theoretical kid would be. But if say they went to a museum and this exhibit is tailor-made for them, and the other people are like, why is this so exciting? Like, this is super duper boring. Like, only you would like this. There might be some people that are like, kind of. So this would be like a non-specific binder, but most of the stuff is just going to go right through. So these kids are going to be coming out on like that first bus. So they're going to be separated from our protein. And so they're going to go straight through. But then eventually you need to get your protein out. And so what's going to happen is they're going to have to kind of like bring in security to get these kids out, and the security is going to take the form of a competitor. And so basically this competitor is going to compete for the spot on the beads. So basically this competitor is something that you can think of it as like a security guard, but really it's more like displacing them. So the security guard stays here and they just like yell at the kids to get out or something. You can also think of it, so like this is similar to with ion exchange, but here you're using charge as the special quality and salt or pH as your security. And so in either of those cases, you're pushing your thing off, or when you're doing the pH change, you're basically making it so that you don't like the exhibit as much. So maybe someone tells you like, oh, did you know that there's a typo there or something, and you're like, oh, I don't really go. But really what proteins, because their charge is going to depend on the pH, if you change that, they're going to stick differently. But otherwise, it's like kind of like bringing in people that like the exhibit even more. And so if they like the exhibit even more, then they are going to like displace you from the exhibits. They're going to push you aside and then take your place at the exhibit, and so you don't get to see your favorite exhibit anymore. But because you're kind of when you're doing affinity chromatography, you kind of just like send them all at once. Like send in all this like this rowdy group of kids that really, really love protein purification come in. And so everything's going to get pushed off at once. But because with affinity chromatography, you typically have some like really, really specific feature, then only your protein and similarly excited. So proteins that like non-specifically bind to their things. So this is why we use like affinity chromatography for this capture step, this first step, because it's going to be like the most specific for our protein. If we have some sort of specific feature about our protein, that it should be like perfectly specific, but nothing's perfectly specific. And so we're going to have a little stragglers, but not much. And so this is why we use this like affinity chromatography capture step. We can even then like cut off the tag often because now it's no longer useful to us. And now we can rely on things that are inherent to the protein. So in some cases, there's something about the protein, like maybe you have an antibody against the protein itself, or maybe it binds to some substrate and then you put the substrate on the resin. But in a lot of cases, it's going to be some sort of tag that you put on. So it's kind of like you're brainwashing the little kids to really, really like this exhibit before you send them through there. So you make them like this exhibit and then you put that exhibit in there. So it's like perfectly matched and your protein will stick. Other things won't stick. And then you can compete off your protein. Because you had things that non-specifically bound, now what I do with my protein is I take it through ion exchange chromatography. And note that you don't have to go through all these steps depending on how pure you need the protein, what your goals are with it and that sort of thing, and how pure it is coming off of here. Sometimes it's really pure coming off of here, sometimes not so much. If you cut the tag off, then you're going to have to like remove the tag, and so this ion exchange can help with that if you can't get it off with size exclusion, and much more on this in other posts, but today I'm just having a little fun. So you take the things that this output from here, and so now you have your kid is mostly alone, but there's still some kids there, and so now you would do the ion exchange, and here you're relying on something that's kind of inherent to all of proteins. All proteins have charged regions, even proteins that even if you use your protein is overall negative, and so you use a overall positively charged resin. So this would be like an anion exchange column. Even proteins that are mostly positive, they're going to have some negative regions. And so basically the point is that this is something that's inherent to all proteins. So it's kind of like something that everybody likes to some extent, but not that much. And therefore we can take advantage of this to send in people who like it a little more and then a little more and then a little more. So we can do like a gradient elution type of thing when we're progressively adding more and more salt, and to push like our thing up. So it's like gradient elution. This would be kind of like if you had a tracker on like when buses arrive. So this would be like the UV chromatogram or chromatograph. I can never remember. But basically when your protein is coming off of the column, this active, it's going to go through this UV detector. Proteins detect UV light, and so you're going to see a signal. So this would tell you like, oh, a kid just left the museum. And then you would look and see what bus the kid was on and which fraction it came into. So it's really hard to imagine that someone loves protein purification more than me, but if someone liked it more, and then they would push me off at the museum, and that would be the idea. And so if there was if there was another protein that also really liked it and was still stuck with me, then we could potentially separate those using size exclusion chromatography. So we've taken advantage of the special feature with affinity chromatography, so the fact that I really, really love protein purification. And then we took advantage of the fact that I had some property that everybody likes. Maybe everybody likes dogs. No, everyone doesn't like dogs, which is really sad. Everyone likes something. I don't know. People can never agree on things, it seems, but there must be something that everybody likes to some extent. And that would be what you would see for something like ion exchange. But in those cases, you're actually like stopping at the exhibits and reading the placards, and taking as long as you could on purpose because you really like those exhibits. And so this is like when I would go to a museum with my parents as a kid, and I would stop at like I would be in there for a really long time, and they would stuck at an exhibit I really loved, and then they'd be super duper bored. So they would like wait for me outside sometimes, like go get ice cream or something while I was still in there. So that'd be like affinity chromatography. and ion exchange. But the case is different with size exclusion chromatography. Here, the museum exhibits are really boring, even for me, who is like loves learning. These exhibits are like super duper boring. And so instead of actually stopping and reading all those placards like I normally would, I would just want to go as fast as I can through this museum. But the problem is that you have to go through every exhibit that you have access to. And so if you have access to an exhibit, you have to go through it. And basically this is, the bigger you are, you can't, if you're too big to get through the exhibit door, then you can't go through the exhibit. But if you're small enough, then you got to go through it. And so these little proteins end up going through more of these pores. And so they can, I kind of show them going straight through, but they don't necessarily go straight through. They can come like in and they get stuck. It's a dead end. They go out, they go in, they go out. More on this in my post. And that before, basically there's this pores in the bead that they're getting. And the bigger guys don't have to go through as many. And so they're going to take a shorter route through. And therefore they're going to come out quicker. The bigger you are, the quicker you come out. And so you're going to be on one of those earlier buses. So at the end of the day, you can pick up your protein all alone. And yeah. So I have a lot of content on protein purification and protein chromatography and more serious content. I have a bunch of practical videos on YouTube and all of this sort of thing. But today I just wanted to do something a little fun. And yeah, I don't know if this analogy works for anyone, but it was something that was when I was first learning about chromatography, it just like popped into my head. And so this is some refresh content from the very early days of the bumbling biochemist. So I hope it was a little fun for you too.